Okay, so here's a video about how the different frequencies make up a signal. And before we can filter the signal for different frequencies or different frequency content, you should understand what it means to have a signal composed of frequencies. So if you follow along, it's really simple. You start by generating this time column in 0.1 second intervals, or just a sequence of number that goes up 0.1 each time for each frame. Now the first signal is this column. We're generating it by simply saying that's the sine of that time signal. So the sine value of the time. The next signal is the sine value of the time multiplied by 3. So 3 times this cell. The next signal is the sine of the time signal, here this one, multiplied by 10. And we're adding this factor inside the brackets to give it a higher frequency. So as you can see, this one is the initial sine wave, this is a slightly higher frequency, and this is an even higher frequency. This is 3 times the frequency, this is 10 times the frequency. So then we are forming the sum. So take a look, this is a sine wave, a slightly faster and an even faster. So we take the first signal, this one, and we add this signal to it, then we get the sum. Well, I didn't add the full signal, I just added parts of it, so you can see. So this one is the signal, the first sine wave, and then we add 0.2 times that third wave to it, and that gives me that sum. Let's take a look at that sum. What you can see here is that it's kind of a sine wave, but there's a sine wave on top of the sine wave. And if I showed you that and I would ask you, well, what's the wavelength? What's the frequency? You'd have a hard time intuitively looking at it. And you would go like, well, there's 2 big waves and 4 waves here, but there's also the smaller wave. So what is it really? Well, the answer is it's both. If you put this sine wave to an audio speaker, you would hear both tones. A musician, or at least a professional musician, will understand what I'm talking about. But if you're a total noob to this, then this might be surprising that there's actually both sine waves contained in this signal. That's the reason why sometimes people talk about the frequency domain of a filter. So in the time domain, you just see the line. But in the frequency domain, these 2 frequencies would show up independently as little spikes. So this signal contains both frequencies pretty much, well, not equally, but the amplitude is the large signal is there and the other one is also there. And this signal pretty much contains both of these frequencies to a certain degree. So let's take a look at this composed signal, the thing that contains the 2 waves, basically. So in this column here, I have a low-pass filter, and what we have is we take the sum and then we filter it, which means we're doing exactly what we've done before. We're just taking the new signal, which is now the sum, that's our signal, and multiply that by the adoption rate, and then we add the previous output, the previous filtered value, and multiply that by 1 minus the adoption rate. You can see it up here in the formula, the adoption rate is up here, so that's what populates this column of numbers. Let's dial down the adoption rate and that way crank up the filters. So we're at 100%, that means there's no filtering taking place. Go to 60 probably. Take a look, you see how that new line kind of smoothens out and departs from the original. Let's go maybe like to 30%. So you can see that orange line, it doesn't have all these smaller peaks anymore. It gradually becomes smoother and smoother. It means that this high frequency wave gets filtered out. It's no longer allowed to pass, whereas this low frequency wave is allowed to pass. That's why we're talking about a low pass filter. Low frequencies are allowed to pass, at least to a much higher degree than the high frequency content. So you see that orange signal, I mean, it still has some waviness, so we're not filtering out all of it. It's just that the amplitude of these small waves gets squished down. It gets attenuated a lot more than the bigger one. So let's crank up the numbers, or let's crank up the filter even further, maybe a 10%. Adoption rate will give you a pretty smooth sine wave already. So there's barely anything of that high frequency signal still left. And there's still a lot of this initial low frequency signal still present. Again, you see how that peak is drifting away. The peak used to be here, now it's here. And the higher I set the filter, for example, on a 5% adoption rate, you can see that the peaks, they move over there, they come later, and they also not as high. So you need to send that signal through another gain to bring it up to its original level. Yeah, I hope that gave you a little bit of an insight into low-pass filters and how they behave in the time domain. And yeah, play around, try to recreate this Excel file on your own, and start playing around with the adoption rate, and you will see how you can, what happens to different frequencies and what happens to different shapes of curves after you send it through a low-pass filter, at least through a first-order low-pass filter. Because in the next video, I think we will be talking about the second order, which basically means if you put through two low-pass filters, one after the other, what happens to the signal.